Hi everyone, my name is Thomas, and the topic of this project is Big Data Predictions in Meteorology. Weather is something that affects all of us, from determining whether or not it would be nice to go for a walk, to affecting our food supply, or, in an extreme case like this, requiring us to seek shelter. The weather can adversely control our day-to-day activities. Extreme weather is also expensive. Superstorm Sandy was estimated to cost $50 billion in damages, and Hurricane Katrina cost $128 billion. The tsunami in 2004 cost over 200,000 lives. Given all of that, it would be very helpful to be able to predict what the weather was going to do, if only to be able to prepare for it. Human civilization has tried to predict the weather for a very long time. The ancient Upanishad scriptures make reference to weather predictions, as do records from ancient Babylon. Aristotle, unsurprisingly, had something to say about this topic too, and wrote Meteorology, considered to be the foundation for modern weather forecasting. However, it wasn't until the last century or so that weather prediction became more of a science and less of an art. The problem is that the weather depends on many variables. It is affected by local variation in time and space, atmospheric pressure, the presence of mountains, bodies of water, the wind speed and its direction, clouds, and other factors. The National Weather Service and National Oceanic and Atmospheric Administration, the NOAA, which are the U.S.'s current national entities that handle weather, collect tons and tons of weather data from sensors all over the world, and they put all this information into their models, which can predict the weather up to 3 to 6 days in advance. This data is archived and publicly available, along with their forecasts. If you're interested, you can go to this website and dig around for their datasets. My original plan was to download a few of these datasets and run predictive analytics on them. However, these datasets are in files that are prohibitively large, and my dinky computer was never able to complete a download. Also, the data seems to be formatted in a way that requires further processing before doing any analytics, and there are a ton of concise code names that you would need to understand before working with the raw data. Luckily, there's an R package called RNCEP, which interfaces with the government's database and allows you to pull subsets of the weather data, pre-formatted into numeric arrays that you can then manipulate in R. This solves both the dataset size problem as well as the decoding and formatting problem. This package is on CRAN, so if you already have R installed, you install and load this package just like you would do with any other package. Using this command here, I grabbed surface temperature for a 5-degree square grid in latitude and longitude around Boston for every day from January 1st, 2009 to December 31st, 2013. The grid is sampled at 2.5 degree intervals, so this code gives you a 2x2 array in space times n time points, which you can see here. The NOAA samples this information every 6 hours starting at midnight, 6 hours, 12 hours, 18 hours from midnight, which you can see here in the labels. The temperature readings are in degrees Kelvin, which I converted into degrees Fahrenheit. The RNCEP package can do a lot more than just surface temperature, and if this topic is interesting, I recommend you read the documentation, which is well written and has many examples. The first thing I did was to plot the temperature as a function of time. While I'm on the topic of plotting, I also loaded a popular package called ggplot2, which gives you a lot more graphical capability on top of what R can already do. I'll need this for later when I plot multiple things on top of each other. I plotted only the temperature readings from noon to simplify the problem. As you can see, there's a clear periodicity in the data, which corresponds to about a period of a year. To predict this data, I used a very well-studied model called linear regression. Unlike the naive Bayes model in Mahout we used recently, which classifies and predicts a categorical variable such as cats versus dogs, regression predicts a continuously varying variable, which is appropriate for our temperature data. Linear regression takes on this form, where the output to be predicted is a function of a constant term, a weighted sum of some predictor variables, and an error term. The error term is assumed to be a random variable of the error magnitudes and is normally distributed with zero mean. Now the question is, what predictor variables do we use in this case? We can't use time or number of days directly because temperature is not a linear function of time. Instead, we'll need to transform the input, number of days, into a time-varying waveform like a sinusoid in order to account for this periodicity. To do this, first I extracted the data and put it into a column like this. Next, I used the fast Fourier transform to figure out exactly what sinusoid to use. The FFT decomposes any time-varying waveform, such as the data, into a weighted sum of sinusoids, and here on this plot, I've shown the relative power of each sinusoid present in the data, increasing here in frequency. You can see a clear peak at this frequency, which happens to correspond to a period of 1 year. Now that I can transform my input from days into a sine wave, which you see here, I can fit the regression model. I actually fit two models. The first just uses the mean of the data to predict the data, and the second is the regression model. I could have used Mahout to do the fitting, but R has very convenient linear regression methods built in, which I use out of convenience. After I fit these models, I plotted their predictions on top of their data. Here's where ggplot comes in handy. On this graph, you can see the mean of the data plotted in blue. It does a poor job of predicting the data, but at least this is not a bias prediction where it's consistently above or below the data. On this graph, I've overlaid the predictions of the regression model in red, which you can see goes through the data nicely. It seems to capture the periodicity pretty well. However, the predictions don't capture everything in the data. For example, at the extreme temperatures, the model fails to account for very short-term, quick fluctuations in temperature, which I've circled here in blue. Also, there are day-to-day fluctuations that aren't captured by the overall year-long periodicity. To look at measures of my model fits, I can't use classification accuracy like we did with the naive Bayes exercise. Instead, I compared the amount of unexplained variance, that is, the amount of variation in the data that the model does not predict. The unexplained variance of the average temperature model is the same as the variance of the data itself, which gives us a baseline of the amount of variation to explain in the first place. Here's the amount of unexplained variance of the regression model. This variance, expressed as a percentage of the total amount of variance, is about 22%, which means that the regression model accounts for 78% of the variance. This is pretty good for a very, very simple model, but keep in mind that this is just training data, and if we apply this model to predict new test data, it will not do nearly this well. I also checked that the error magnitudes were normally distributed with zero mean, which is the case. Real models used by the NOAA and other weather services rely on nonlinear differential equations called the primitive equations to make their predictions, and while I couldn't find the exact models themselves, Wikipedia has a nice article on these equations which can't be solved analytically and require numerical approximations. It's been many years since I had any hope of understanding differential equations, so I leave this to the interested viewer. There are also attempts to increase forecastability beyond the 3 to 6 day range we currently have. IBM, for example, uses its Deep Thunder software and its massive supercomputers to simulate the weather and to make predictions out to 2 weeks. Figuring out how to parallelize the primitive equations will be the key to taking advantage of MapReduce and increasing the power of weather predictions. Thank you very much.